Okay, welcome back. So, how was your main set? Good, bad, or ugly? Is anybody going to answer that?
So it was average.
Average. And the degree of difficulty of the questions?
Yes, sir, it was average. The difficulty.
Difficulty was average. And performance?
So actually, I think I could do more if you if it was more time.
Time consuming. Okay. Okay,
Yes.
fine. Okay, fine. So maybe in my next class or so, I'm going to discuss about the questions and how you guys have answered to that. But I think I have seen some improvement over quiz one. See, it's about how you are going to treat the questions. It is not about the degree of difficulty of the questions, but I'm going to look into how you are answering the questions, whether you have been able to cater to all the attributes that I'm expecting from you. Okay, so I'll explain this to you in a later class of mine. So hopefully today's class is going to be the last class in series solution. So because as I have told you, if I go on and on, then this is going to go into an infinite loop. Okay, series solution. So I would like to finish series solution today, and then from tomorrow onwards, I'm going to move over to system of first order equations. System of first order equations, and over there, I'm going to do your autonomous system, and from there, I will try to introduce into the stability of a solution. So basically, the dynamical system concepts, you are going to get a hint from there. Okay, fine. So today, what I'm going to do, I'm going to start with your Gauss's hypergeometric equation. Gauss's hypergeometric equation. So you may be thinking why I'm particularly interested in this equation. I'm not sure whether you have already tackled it or not. So during the course of dissecting this equation, you would find out that the way the equation is structured, many well-known equations can be put into that form, and you can bring many different solutions. Not really many different solutions. Solutions of different second order linear equations into a particular format. It has a fixed format, and from there you can derive many of the stuffs from one thing. Okay, so basically it brings many of the solutions under one umbrella. That is why I thought that it would be worthwhile for you to study this equation, and for that matter the solution of this equation, and it is going to be useful later on. Okay, fine. So Gauss's hypergeometric equation, so it is if we are given in this form, say x 1 minus x y double prime, and the next part is you have to be attentive in the next part. Okay, so y prime, and of course there will be something like this. So here, just concentrate here. So this is into x, and this one is AB into y, and where we are assuming that A, B, C are real constants. Okay, A, B, C, they are real constants. Okay, so now look at the form. If you look at the coefficient of y double prime, it is a second order polynomial, second degree polynomial. Okay, and if you look at the coefficient of y prime, it is a polynomial of first degree, a linear polynomial. Okay, fine. So now, if I want to find out, if I want to convert it into your this normal form, you know what the normal form is. So today I am going to skip many of the steps because you are already aware of many of the stuff. So I'll just straightforwardly get into the final expression, and then in the meanwhile I'll tell you to do the remaining part as a homework. Please bear with me. And don't think that I am doing the easier part and I am leaving the harder part for you. It is not like that. Okay, fine. So you know that here your px, it is going to be your c minus. This is a plus b plus 1. Sorry, this is not b minus 1. A plus b plus 1. This x into this divided by x into 1 minus x. Okay, so that means if you want to find out x px, simply this x is going to go. Is it okay with everybody?
Yes, sir.
Right? It is. It will be like that, and then what is going to happen? If I expand it 1 by 1 minus x, this is going to give me 1 plus x squared and so on. And from here you will see that my constant term is c, and then it is going to be something like this, c into x, then minus this into x. So it is something like, it is going to be something like this, c minus a plus b plus 1 x. So the same coefficient is going to continue. You check whether I'm right or wrong, but I'd be interested in the very first constant term here. Okay, so basically for this, as a power series about x equal to 0, what I have got from here, I have got p naught to be equal to c. So for me, that information is important. P naught equal to c. Is it okay? Fine. So similarly, if I find out qx is again your minus ab, and this is x into 1 minus x. So that means x squared qx is simply going to be abx into this. Is it okay with everybody? Fine? Okay?
Yes, sir.
Yeah?
Yes, sir.
Fine. So this is minus abx, and again 1 plus x squared, etc. And from here you will see that the constant term is absent here. So basically what I am getting q naught equal to 0. So that information is good enough because I don't want to go into detail. These are good enough because I want to directly jump into the initial equation. Probably you have already got a hint for that. Okay, so these two are good enough for me. Okay, so now let me. So obviously, now the initial equation is going to be given by m into m minus 1 plus p naught m. So this is cm plus q naught equal to 0, right? And q naught is 0, so this is equal to 0. Okay. So from here you can see that if I take m common, this is equal to 0, right? And this gives me the root of the initial equation as m equal to 0 and your 1 minus c. Okay, so now let us concentrate here. Okay, so I have taken the details from Simon's Go, but one comment made there, I'm not very happy with that. So, see, now I have got two roots. Whether those two roots are equal, whether they differ by an integer, or whether they differ by a fraction, it doesn't matter uh, on the existence of the first solution as an infinite series, isn't it? Irrespective of whatever happens, definitely I am going to have a power series solution, right? Is it okay? You are getting my point, right?
Yes, sir.
Right? We already had a theorem. That theorem guaranteed at least one power series solution. But in Simmons, he has made it a bit confusing, because what he has done, let me tell you, like say, now if you look at the second root, if you look at the second root, I know that if the difference between these two roots is 0 or integer, then I'll have to look for something else, right? It doesn't guarantee you the existence of the second infinite series. So here, the difference between the two roots is simply 1 minus c, right? So that means if c is 0 or a negative integer, if c is 0 or negative integer, so that is going to make the difference between these two roots, m1 minus m2, as a positive integer. Right? Is it okay? Fine. Now, what Simmons has written in his book, there is a one particular line that if this does not happen, then we can get a series solution from theorem, whatever theorem he has projected, theorem A on chapter 28 or something like that. But irrespective of whatever happens to this, I am going to come back to that later on. Whatever happens to this, I am always going to get a series solution corresponding to this root m equal to 0. That is what my point is. Is it okay with everybody? Right? You please check in Simmons' book and then let me know whether I'm right or wrong. Okay, fine. So now let me come. I'll come back to this later on again. So obviously, corresponding to the first root, I can have a solution of this form: x to the power 0, n equal to 0 to infinity, a n x to the power n. And I'm not going to put it back into the original equation, that is Gauss's hypergeometric equation. So you got to believe me that if you plug that in, then you are going to have a recurrence relation of this form. Okay, and I am leaving that part. I am leaving this part as a homework. Please try it at home. This is homework. So that once you plug this in the Gauss's hypergeometric equation, plug this in the Gauss's hypergeometric equation, then you come up with this reference formula. So this is your homework. Okay, fine. So now something very interesting stuff is going to come out of this. Okay, fine. So now when you are going to plug in n equal to 0, so then A1, this is going to be AB into 1 into C, right? A naught. And remember, we are going to assume A naught to be equal to 1. Because I have already explained it. I mean, whether you expand this series, just keeping A naught as non-zero or A naught equal to 1, it doesn't matter, because eventually in the general solution, when you are going to express it as a linear combination of, like here, two solutions, then it is going to be accommodated into that constant in the linear combination. Okay, fine. So now, I mean, if I take A naught equal to say simply 1, so then this is going to give me simply AB 1 into C. So then your A2, if n equal to 1, then A2 is going to be your A plus 1, B plus 1, then 2, c plus 1 a1. So if you plug this in the value of a1, then you will see that this is going to give you a b into b plus 1, and then this is going to be 1 into 2, and then c into c plus 1. Is it okay? Fine. So if I continue like this, then you will see that I am going to get an to be your, okay, see, when it was 2, it ended in 2, right? When it is n, it is going to end in n, okay? And then of course, c into c plus 1 up to c what? C plus? Can somebody tell me? I'm clueless.
n minus 1.
N minus 1. That means these are also going to be n minus 1, n minus 1. So basically, so now I can freely write it b into n minus 1, and then this is simply your factorial n, then c into n minus 1. That's it. Okay. So my y1, my y1 is simply going to be y1 equal to this one, 1 plus, maybe I can write it from n equal to 1 to this, and then factorial n one x to the power n. Okay, so this is my first year. This is my first series. Okay, so now I mean, if you want to find out the radius of convergence, so then what you have to do, you have to simply figure out what is a n plus 1 x to the power n plus 1 divided by a n x to the power n is as limit n tends to infinity. So you know that a n plus 1. So you are going to have simply one extra term here, a plus n. Similarly, from here, or maybe let me concentrate here. From here, you are going to get b plus n. Okay, and similarly here, you are going to get c plus n. And what will be the extra term here? Simply n plus 1, because that is going to be factorial n plus 1 divided by factorial n. Okay, fine. So this is it okay? Fine. And this tends to what? This tends to n is everywhere in all the factors, right? Divide by n square. So it is simply going to be mod of s. Is it okay with everybody? Right? Right? Okay. So now another interesting thing will come out of this. So obviously you know that the series is going to converge if this part, this whatever I have found out. I have found out to be mod of x. But if That is, if the ratio of this is strictly less than 1, definitely the series is going to converge, right? Okay, so I can definitely say that y1 converges for all this. Okay, so that means the radius of convergence is 1. So now I'm going to ask you a question here. Say this series that this is a Frobenius series, although I mean eventually it turned out to be only an ordinary power series because the first root we have considered it was m equal to 0. So now that Frobenius series was expanded about x equal to 0. Fine, okay, and we have found out the radius of convergence as 1. Can you tell me why it is so? Yes?
So you can see from the coefficient functions Ex and Qx, when you are expanding this function, then the radius of convergence is 1.
No, how come? How come? Why? What? Yes. Please bring the singular point here, please. Yes.
So one is a single point.
Exactly. See, if you look at the original equation, the very first coefficient of y double prime, that was x into 1 minus x. So both x equal to 0 and 1, they were my regular singular point, if you recall. But I am expanding this series. About x equal to 0, right? So you know that, like say, the radius of convergence is going to be distance of 0 from the singularity which is nearest to 0, right? Because here I have only two singular points, so this is why it is happening. Now, is it okay with everybody? That concept also. Okay?
Yes,
fine. So you can relate this to that also. Fine. So this takes care of the first series solution. So now let me come to, and I hopefully you will remember this. No? You will remember this. I think this is easy, right? There is a particular pattern. This is easy to remember. Anyway, I am here to help you so that you will be able to recall all this stuff. Okay, fine. So now let me come to the second series. Come to the second series. See, and let us assume that because I want to find a second series such that the second series solution y2 such that y1 and y2 they form a fundamental set. And for that, what I want to do, I want to avoid the difference between the roots of the initial equation being a positive integer. Okay, so I have already explained to you under what circumstances they can the difference between the roots can be a positive integer, and it happens when c equal to 0 or c is a negative integer, right? Is it okay? So let us avoid those two scenarios, okay, so that I can get a second independent solution. Okay, fine. So now you know that since my second root is your 1 minus c, so definitely the second series solution y2 I can get it as x to the power 1 minus c, something like this, say n equal to 0 to infinity, something like bn x to the power n. Is it okay with everybody? Fine. So now again I am going to give you one homework. I am again going to give you a homework. What I have done, just a minute. Anyway, it doesn't matter. See, in the book they have written as a n x to the power n. It doesn't matter because eventually you are going to find out the coefficients, and by plugging in the constant term to be equal to 1. So that is why whatever you take, it doesn't matter. Okay, I would rather stick to this one. So now you can do one thing. I am giving you one transformation. Y equal to your J. Y equal to this. Yeah, y equal to this, and then under this transformation, you will see that these equations. Let me write it down once again. This equation. This equation, it reduces to under this transformation. This reduces to your x into this remains the same. Only this part is no, a minus c plus 1 into b minus c plus 1 z. This is equal to j. Okay, fine. B minus c plus 1 z equal to 0. Okay, so now can you tell me something from that? I mean, can I again convert this equation into Gauss's hypergeometric equation for the variable z? Can I do that? Could you figure it out, please? See, here obviously I cannot change these two. Right? If this is capital A, this is capital B, I want this to be in such a way that this becomes something like capital C minus A plus B plus 1 into x. Right? Is it okay with everybody? If I want to change it to the format of Gauss's hypergeometric equation. Is it okay? Fine. So now let us plug this in. A is A minus C plus 1, B is B minus C plus 1. So what has happened? It is 2, this 2 plus 1, that is 3, and then A plus B minus 2C. Right? A plus B minus 2C. I already have A plus B plus 1 here. A plus B plus 1 here. So, what I must do? Yes? Yes, can you tell me? Yes? So, capital C will be equal to
C will be 1 if you compare to
C will be equal to
1.
How come? I already have minus 2C here. You have to balance that minus 2C with C. Isn't it?
Yes, sir.
So
from here we can, I think we should get minus 2C plus C equals to 1. So from there we shall get C equals 1.
no. Okay, let me again. See, this term as a whole, this is giving me A plus B minus 2C. See, here again, 1 and 1 is there. I have got one extra one, right? Plus 3. Okay. So I am already fine with a plus b, which is already here. So I have one extra 2 here, right? This is 3, but this is 1. Extra 2. In order to balance that 2, I have to plug in, I have to bring in minus 2. Just a minute. A plus C plus.
So I think capital C will be 3 minus.
No, just a minute. This is A plus C plus 1. B is B plus C plus 1. And I already have this. This is 3. So I'm going to balance it with 2. And I have minus 2c, but here I have got c, right? So here, so minus, this is going to be plus, okay? This 3 is going to be what? Minus 3 and no, from here I have to bring what? Just a minute. A minus C, A plus B minus 2C plus 3. I already have. So in order to balance this one, this is minus 2C, but here I have C. So it is plus 2C. Basically minus 2C minus is plus 2C. So definitely here minus C will come. Okay, fine. So then I need a 1 here. Here I have this is
it 2 minus C?
Yeah, it is going to be 2 minus C. Yes, it is going to be 2 minus C. Okay, so then it will be balanced, right? Because 2 minus 3, it is minus 1. Minus 1, you just put it inside bracket, then everything will be balanced. Okay, so now I'll tell you what I'm going to do here. Okay, see, I can write this as 1 minus x this is equal to 0. Is it okay? Yeah.
What about x? B plus 1 into x. And there, where is this?
Which one?
Below the next line. A
Yes.
plus C minus.
Oh, just a minute. Just a minute. I didn't work it out. I'm simply balancing this. Just a minute. I think, just a minute. If I 2 minus C. Maybe let me do one thing. I can assure you. I think this is not going to be this. This is going to be just a minute. 2 minus C. No. This is not going to be this at all. Sorry. Anyway, just a minute. So let's keep that one. Okay. So I am giving you a homework. See, you just prove that. Okay. No, I was just trying to backtrack. No, that is not going to work. Yes, you have rightly said, because there is a multiplication by x. It is not simply x to the power 0. See, what you do, what your homework is, you show that under this transformation, Gauss's hypergeometric series, it reduces to this. That's it. Okay? It reduces to this. Fine? So now if this is so, earlier what was happening? If you recall, when I plug in something like this as my series solution, it led me to just a minute, I forgot to tell you one thing. Okay, fine. See, the series for y1, whatever we have got, where the coefficient of x to the power n was this a plus n minus 1. I completely forgot to introduce that symbol. Sorry about that. And then factorial n c plus n minus 1. Okay, fine. See where the series for y1, right? Where the coefficient of the nth power of x is given by this. So this is also denoted by this f of a, b, c, and then x. Is it okay? Fine? Are you getting my point? This is just a symbol. This is just a symbol. Is it okay with everybody?
So why x is there?
Because in the original equation, I have the coefficients as x. This. It will depend upon this. Whatever variable I am going to use here, this x will be replaced by this. Okay. So I will be able to answer this more precisely in my next section, when I am going to use another transformation where I am going to convert x into t. Then it will be more clear to you. Okay. So basically, x is nothing but the independent variable. Is it okay?
Yes.
Fine. So for the independent variable, I give x. See, when I use this series, x to the power 0 into this. Say, suppose here, if I had replaced this with some j's, right? I had replaced this with j. So that is giving me a series solution like this, right? So now for the second part, what is happening when I am replacing my y with this variable, it is converting me into this series, right? So that is why my y2 I should get it as 1 minus c into f of here a minus c plus 1, b minus c plus 1, and then 2 minus c x. I should get it like this. Is it okay? Fine?
Yes.
Right? Okay. So that means a general solution of Gauss's hypergeometric equation is going to be given by y equal to c1 f abcx plus c2 x to the power 1 minus c, then f of two minus c x. Is it okay? Okay, fine. And remember, this series is about the point x equal to 0. This series is about the point x equal to 0. Okay, fine. So now let me that question about why it is x. Okay, fine. So now can you tell me what we should do when I am trying to find a series solution about x equal to 1 using Gauss's hypergeometric equation concept? Can you give me a way? See, suppose I am using t equal to 1 minus x as my transformation. Okay, right? So then, if I can get a Gauss's hypergeometric equation in the variable t instead of x in the variable t, right? Then, if I get a series solution about t equal to 0, that is going to be equivalent to getting a series solution about x equal to 1. Got it?
Yes, sir.
Yes. So now let us see what happens. Huh? So here, if this is so, so then your dt dx this is equal to minus 1, right? So now what is going to happen? What is going to happen? Your dy dx. See the original series. Just give me just couple of seconds. Okay. I think you will be appreciating Gauss's hypergeometric series only through this one, what I am going to do. Okay, so if you recall, okay, and where these y prime, y double prime, they denote your differentiation with respect to x. Okay, so now because I have changed the variable from x to t, that is why now again your dy dx is dy dt dx, right? So this is going to be minus dy dt. Is it okay? Fine. So similarly, d2y dx2. So this is ddx of dy dx. And see again I can write it as ddx of dy dx. I can again write it as ddt of dt dx again, right? Is it okay?
Yes, sir.
Yes. So this is going to be ddt of minus dy dt, and again dt dx is minus 1, right? So this is basically going to give you d2 dt2. Is it okay? Fine. So then this equation, now you can see that your x is going to be 1 minus t, right? X is going to be 1 minus t, and again 1 minus x is t. This I have already found out that dt2 c minus a plus x is 1 minus t, and this remains the same. You cannot change this. Okay. What about this minus? Sorry. So what I can do, because your dy dx is minus dy dt, what I can do, maybe, okay, let it be like this, minus dy dt minus a dy, this is equal to 0. Okay, so this implies Okay. Okay, fine. So now, say, because this is minus dy dt, I can simply think this to be t minus 1, isn't it? I can simply think it to be t minus 1. So now let us bring the constants out. So the constants are going to be your right, t minus 1 and what? This is also going to be minus c, right? This is also going to be minus. Is it okay? Are you able to is there a disconnection? Okay, now it is coming back. Yeah. No, something happened to my computer. But anyway, see, what I did, this was 1 minus t before because this was minus dy dt. So if I multiply everything by minus 1, this is going to be minus c and this is going to be t minus 1. Is it okay? Fine?
Yes.
Okay. So then let us bring the constant term. So this is going to be c minus 1 into this is plus. So a plus b plus 1 minus c, right? And then minus a plus b plus 1 into t. Fine? This is equal to 0. So, yeah, that's it. So, okay, so maybe I can write it as okay, fine. So far so good, right? Is it okay with everybody? The new equation,
Yes.
right? So now, if I want to write down the say suppose I simply call it y double prime, and this is say y prime. So where the prime denotes, I mean derivative with respect to t, right? So then the solution of this equation, so now you consider this to be c, isn't it? Solution of this equation, it is going to be something like f, your AB will remain same, but your C is going to be A plus B minus C plus 1, isn't it? Right? And then it is going to be in the variable t. It is going to be in the variable t. Are you getting my point?
Yes.
Right? Okay. And then what you do? I mean, in order to get the final solution, you simply replace t by 1 minus x. That's it. Okay? Isn't it? Eventually, this is going to give you a series in t, right? So then, what you do, simply replace t by 1 minus x. That is going to convert everything into your original variable x. Okay? Now, another thing I want to mention you is that, see, this is, just a minute. See, this one is corresponding to when the root of the initial equation is 0, right? So, if you want to find out the second rule, so what was that? like say earlier, it was something like 1 minus c, isn't it? The roots were 1 minus c. Right? Right? Isn't it? So here now c is this. Here now c is this. My new c is this. So 1 minus c is going to be what? C minus a minus b, isn't it? Right? Yes?
Yes.
Right? You see, you may be thinking why I am trying to loop in this. So basically, in order to have this second independent solution without any hassle, what we must have, so this what? This must be what? This cannot be a positive integer. Yeah. Repeat my question is, say, earlier in the original equation when I didn't use any transformation. So then this was my C, and the second series solution I was trying to find out something like this. Okay, where the existence of this series was guaranteed only when 1 minus c was not a positive integer. Right? Now what is happening if you compare that situation to this situation, right? Your 1 minus c now becomes small c minus a minus b, right? So if I use that concept again here, so that means you don't want c minus a minus b to be a positive integer. Only then you are going to get the second series solution in the way we are trying to find it out. Otherwise, we have to do something else. That is what I want to say. Is it okay? Fine? Okay? Got it?
Yes.
Okay. So now, let me try to read Legendre's equation. And I don't know whether I'll be able to complete it or not. So I will do, wherever I can reach. And because I'm following Simon's book, the remaining part, you please do it from Simon's book. And if you find some difficulty, just let me know. I'll try to remove those doubts. Okay. So now, this application I'm going to show it to you. In fact, the Rodriguez formula or Legendre's polynomial, you can derive it from Gauss's hypergeometric equation. And that is a very beautiful mathematics involved there. Hopefully you will enjoy it, but I don't think I'll be able to finish it. Okay, fine. So now, let me okay. So now, if you recall, let me write it as n into n plus 1. Why? This is equal to 0. Okay, and of course here, I'm assuming that n is an integer. Okay, fine. So now, just concentrate here. Just concentrate here. Okay. So if I want to convert it, this one into that Gauss's hypergeometric equation, so definitely I would like this 1 minus x squared. I want to convert it into something like t into 1 minus t. Isn't it? Fine?
Yes, sir.
Okay. So can you think about a transformation? Can you think about a transformation? Yes. t equal to something. Obviously 1 minus x will be there, whether something else has to come. Okay, and see, if you take okay, so this is going to work. Let me tell you. I have already worked it out. That is what I know. Okay. See, then what you are going to get from here, your x equal to 1 minus 2t, right? Yeah, x equal to 1 minus 2t. Fine? Okay. See, now here this one is your 1 plus x, 1 minus x, right? Okay. So before working this out, let us do something more. Now again, you will see that your dt dx, that is going to be equal to minus half. Is it okay with everybody? Dt dx is equal to minus half. So that means you are going to get your dy dx. So this is definitely going to give you minus half dy dt, right? And as before, if you follow the procedure as we did it in our last example where I have taken t equal to 1 minus x. So then this is going to give you minus half into minus half, that is 1 by 4 d2y dt square. I don't think I have to work this out. You understand, right? Is it okay with everybody?
Yes.
Yes. So now let us look at this. This is simply 1 minus x, 1 plus x. Okay. So then from this transformation, you can see that your 1 minus x is 2t, right? And then 1 plus x, that is going to be 2 minus 2t, right? If you add 1 to this is going to be 2 minus 2t. So that means 2 into 1 minus t. Is it okay? Fine. And then from this 1 by 4 dt2. Is it okay? Fine. So then what is 2x? 2x is 2 minus 14. Yes or no? 2x. Okay. 2 into 1 minus 2t. Okay. And this is minus half dy dt. And then let it be as it is. Okay. So what does it give you? Obviously, you should be happy that t into 1 minus t I have got. Right? Okay. So again, now let me simply write it as y double prime, where now the prime denotes derivative with respect to t. Okay. So then this is going to give me plus this 2 goes out 1 minus 2t y prime. This I am leaving for you. You will get the hint from there. Okay. Okay. So in order to convert it into Gauss's hypergeometric equation, so now can you tell me what I'm giving you a hint. A, B are those. So A equal to minus n, B equal to n plus 1. Okay. Fine. So A plus B equal to what?
1.
1. See, I want these two as a plus b plus 1. Was it or yes?
Yes, sir.
Yes. So I already have that, isn't it? Because a plus b is 1. 1 plus 1, 2. This I have already got. Isn't it? Right? So C must be equal to 1 itself. Isn't it? Is everybody getting that?
Yes, sir.
Right? So, okay, fine. So, the solution of this equation about the point t equal to 0, about the point t equal to 0 is what? F minus n plus 1, 1 and t. Isn't it? Right?
Yes, sir.
Right? So now, of course, t is 1 minus x by 2. Fine? 1 minus x by 2. I have to simply substitute it there. So let me try to find out the nth term. Okay? Let me try to find out the nth term here for this series. Okay, so your an was what? Let me again get back to this. An was a into a plus 1, a plus then factorial n, and then what? C into c plus 1 up to c plus n minus 1. Okay, so here a is, okay, so this is a is minus n, minus n plus 1, ultimately minus n plus n minus 1. Okay, fine, and then b is n plus 1, right? So let me just put a second bracket here, n plus 1, n plus 2 up to n plus 1 plus n minus 1, right? Okay? Is it okay with everybody? The numerator. So far so good, right?
Yes.
Yes? Okay, fine. So then here obviously factorial 1, and then here c equal to 1. So 1, 2 up to, okay, fine. So now see some pattern is coming up. See, now here from the first brace here, from the first brace, if I take, see, eventually this is going to be minus 1. Okay, so if I take, if I, and see, similarly the previous term would have been minus 2 and so on, right? So had I taken minus 1 out from each term, that would have given me minus 1 to the power n, right? And then I would have what? If I start from here, then 1 into 2 into up to this term, this is going to be n. Is it okay? Fine? Yes? And then you see this is continuing up to n plus 1, n plus 2 up to 2n. Isn't it? So that means in the numerator, I am going to be left with minus 1 to the power n factorial 2n. Is it okay with everybody? Yes?
Yes, sir.
Right? So this is going to give me factorial 2n, and of course you know that this is going to lead you to 1, 2 up to n. This is factorial n. I have another factorial n here. So this is factorial n whole square. Okay, fine. So that is why the solution to Legendre's equation is going to be given by your say y. This is equal to x plus n equal to 1 to infinity equal to whatever. Let me write here. Y equal to 1 plus n equal to 1 to infinity, and this is n squared, and this is going to be your 1 minus x by 2 to the power n. Is it okay? Fine?
Sir,
Yeah.
so in the Legendre equation, n is fixed now.
Legendre's equation what?
N is fixed.
N is fixed, okay.
So, but here we are confusing n with that n, summation n 1 to infinity.
No, I am going to curtail it later on. Don't worry about it.
Okay.
I am going to curtail it. Yes. Yeah, I am definitely going to curtail it. See, I understand your view. So depending upon what n we choose, right? The series terminates, isn't it? This series terminates, and eventually it becomes either an even ordered series or odd ordered series, isn't it? Fine. I'll come to that. I don't know whether time will permit me or not. But I'd like to reach to something. See now, you see another thing. Now see, if I change this one to x minus 1, if I change this one to x minus 1, then I will have minus 1 to the power n coming here, right? From here, this is minus 1 to the power n, x minus 1 to the power n, right? Is it okay? Fine. So this one along with this one, minus 1 to the power 2n. So I can remove. So that means I can remove this and simply write this as, say, let me bring 2 to the power n here, and I am simply writing as x minus 1 to the power n. Is it okay?
Yes.
Fine. So if I want to write down, the new an, say, new an, so I can write it as again. I mean, there are a lot of stuff here. Okay, so for the time being, this is the solution of Legendre's equation. Okay, let me see how much time do I have. Okay, just fine. So I will just give you the second series solution. I'll just give you the second series solution, and then please remaining part you please follow. I mean Simon's book. I mean from page 337 onwards. 337 onwards from Simon's. I have a printed book, so I mean in your PDF. I actually don't know whether it is going to be that, but you'll be able to find it out. So let it be like this. Let me try to find out the second solution, and then I am going to tell you something what further study you'll have to do. Because I'm running out of time. Okay, now from the solution itself. So these corresponded to the root of the initial equation m equal to 0. Fine. Can you tell me what is the other root of the initial equation of Legendre's equation?
It is again 0.
It is again 0 because this is C, right? Is it okay? Everybody getting it? This is C, right? The other root was 1 minus C, okay? Right? So since the roots of the initial equation are equal, so that means I must try to find out the other series solution from this concept, your Vy1, right? Where your V prime is given by 1 by y1 square e to the power minus okay. If I say suppose I write it in terms of t itself, in terms of t itself. So if you recall that pt would have been fine. Is it okay? Because y double prime,
Yes.
right? It had this coefficient. Okay, so y1 square e to the power minus, and this is very well set up. T minus t square dt. Intentionally, I am keeping it like this. Y1 square e to the power minus ln t minus t square. So that this is going to be 1 by y1 square. So this I can write it as t to 1 minus t, right? Okay, fine. Should I write it? I can write it like this. Okay, fine. Okay, so now if you recall the series for y1, the constant term was 1, isn't it? Constant term was 1. Is it okay with everybody?
Yes.
Fine. Here the constant term was 1, and again this one easily I can expand it as a series solution about t equal to 0, right? And since the constant term of here is equal to 1, so obviously the expression within the bracket, within the square bracket, it is going to be analytic about t equal to 0. Is it okay? Because this series is non-vanishing at t equal to 0, right? So as this one, I mean, forget about this being a series. Like suppose this is a function in t, So both these functions, they are non-vanishing at t equal to 0. So obviously, I should be able to express the term within the square bracket as an what power series about t equal to 0. Is it okay? Fine. So that is why this one I can easily write it as this one. I can easily write it as here this. This is equal to 1 by t, and then something like a naught plus so on, right? So, hey, this is not x, this is t, sorry. Okay, fine. So that means your v is going to be a naught ln t. Just a minute. I did one mistake here. Yeah, so this is going to be a1, right? And then a2t. Okay, fine. So then a1t and so on. a1t and so on. Okay. So the solution I am going to get is going to be something like this. Your y equal to c1 y1 plus c2 y2, where y2 is given by v y1, and of course v is given by this. Is it okay with everybody? Right? The only thing is that whenever you are going to consider a series about t equal to 0, so that means t equal to 0 corresponds to x equal to what? X equal to 1. So if you want a solution which is bounded near x equal to 1, then you must plug in c2 equal to 0. Okay, so I think I am going to stop here. Just one last thing I want to tell you is that somebody was asking me about Legendre's polynomial. So Legendre's polynomial. So in terms of the solution of Gauss's hypergeometric equation, what it does, see here Gauss's hypergeometric series, something like this, something like say ABC X. This I consider as an infinite series. But if the series that we have got through this solution f minus n plus 1 then 1 minus x by 2, right? If I curtail it up to the nth power, I write this with this symbol. I write this with this symbol. Okay. So basically, what I will do, I will go from 1 plus up to that an into x to the power n only. And you know what is an, I had already worked it out. Are you getting my point or not? So, what is going to happen? Your Pnx, it is simply this minus n plus 1 minus x by 2. Okay, and you already know the infinite series. Corresponding to Gauss's hypergeometric equation or Legendre's equation, right? So what you have to do, you have to simply curtail the infinite series, or basically what you do, the nth partial sum. Okay, so nth partial sum of the Gauss's hypergeometric series corresponding to Legendre's equation is nothing but Legendre's polynomial of degree n. That's it. Is it okay with everybody? Fine. And you please complete this page 337 to 340 yourself. That is pretty straightforward. Huh? Only at a couple of places, you may have some confusion, but you, try to work it out systematically. It is going to be all right. Is it okay? Fine. You'll be able to study on your own. Yes.
Yes, sir.
Yes.
Okay. Thanks. Hopefully you are not going to skip that, because you will see that the Rodriguez formula you can arrive at through this concept. Okay. And who knows, maybe I am going to ask you some question on that in your next quiz or NSEM. So then let me finish my